So now today we'll start with the mixed grouping of the cells. So it is like this. Yeah. So this is the diagram which we are going to read it. So here we can see that there are number of cells which are combined in series, and there are number of rows also. In each row, see, there are, let's say, n number of cells are present, which are connected in series in a row, and there are, say, m number of rows. So we can say that there is total of m into n, or let's say we have n number of cells over here. N number of cells are there. Sorry. And m number of rows are there. The total number of cells will be, so total cells will be n into m. Total cells are n into m, and EMF for each cell is, say, E. EMF of each cell equals, say, E, and internal resistance of each cell is, say, R. Internal resistance of each cell, say, small r, right? And external resistance we have, as shown in the figure, this is R. External resistance is equal to, say, R, right? Now, since total resistance of all the cells present in series is, say, NR, and M number of series they are connected in parallel, and the internal resistance of the whole battery we say R1. Let's say the internal resistance of the whole battery, internal resistance of the whole battery is, say, R1. R1. Fine. Now, all the series, they are in parallel. Each series has n number of cells, and there are m number of rows are present, or there are m number of series in which these cells are present. So there in total, if we are to find the total internal resistance, that will be, we can calculate it by parallel, that is 1 by R1. This is equal to, so 1 by NR. This is of first series, then we have second series. Fine. So plus 1 by NR, right? So this goes up to m terms, because there are m number of rows are there. So goes up to m terms, right? So total internal resistance will be equal to m times m by NR. Or we get R1 as, which is the total internal resistance. This is equal to NR by M. Fine. And total resistance in the circuit, total resistance of the circuit, this is equal to total internal resistance plus the external resistance. Total internal resistance is NR by M, and the external resistance is, say, R. This is R. That's the total resistance we have. And current I flows through this. This is the current I flowing through this circuit. So that current I is equal to, so we have a current I flowing in the circuit. So external circuit. This is I is equal to total EMF, because total EMF we have, EMF for each cell is E, so we can write here total EMF of total EMF will be N times E, because there are N cells, so total EMF is N times E, so here we have N times E divided by total resistance, which is equal to NR by M plus R. Right? So this goes, this will give me N ME whole divided by, this is, say, NR plus MR. That's the total resistance. To get maximum value of current, the value of this resistance, which is in the denominator, or the denominator factor, should be the minimum. Here we have in the denominator, we have the resistance, which is the total resistance. Fine. The value of this resistance should be minimum. So we can say that for I to be maximum, for current I to be maximum, the value of this resistance, which is NR plus R, should be minimum. By the way, should be minimum. That means the value of NR, we can find it by NR plus MR. This can be written as say root of NR minus root of MR, the whole square, right? The whole square plus, now when we'll solve it, we'll get NR minus 2 root N MRR plus MR, right? So this is equal to plus root of 2, then root of MNRR. That's the total value. For this value to be minimum, this quantity has to be minimum, and the square cannot be negative. The minimum value should be 0. Means you may write it as NR, or for NR plus MR to be minimum, the quantity, which quantity? This one. So this should be minimum, right? So this being the square cannot be negative, hence its minimum value will be 0. So we have root of this is equal to 0. This is 0, or it can be written as root of NR is minus root of MR equals 0, or root of NR equals root of MR. So we can cancel root on both the sides, so we get NR is NR equals MR. And from this, we can calculate the total external resistance R, which is equal to NR by M. Right? So NR, but NR by M hai, this is equal to our internal resistance. Fine. This is the internal resistance of the whole battery. That means in mixed grouping, current in the external circuit will be maximum when internal resistance is equal to the external resistance. Right? So we can say if we substitute this value of R in this equation here, right, we can get the maximum current in the external circuit. Right? Let us substitute the value. So we may write in mixed grouping, the current in the external circuit will be maximum when the internal resistance of the battery is equal to the external resistance. External resistance. So substituting NR by M equals to capital R in this equation, yeah, we may write here in say I equals to MNE divided by plus MR. Right? So on substituting the value, we'll get the current I. This is equal to the NE by 2R. That's it. Now we are going to study the most important topic of this, which is Kirchhoff's law. 3 marks, some numerical will be asked on the basis of this. So Kirchhoff is actually, Kirchhoff's law is used to find the current amongst the different conductors of some complicated circuits. Fine. So these laws, there are 2 laws of Kirchhoff. First law is called the junction rule. Right? Kirchhoff's first law is called the junction rule. Fine. So what does it say? It says that in any electric circuit, the algebraic sum of the currents meeting at junction is in the circuit is 0. That means sum of all the circuits is 0 at the junction. Like here, O is the junction, and we have 5 values of the current given. Say I1 is coming inside, I2 is coming inside, I3, I4, and I5. They are shown that they are going out. So the total incoming current should be equal to the total outgoing current. That means total incoming current should be equal to total outgoing current. Total incoming currents should be equal to total outgoing currents. This is first law or junction law because it is dealing with the current. So we can also call it as KCL or Kirchhoff's current law. I may write here, or Kirchhoff's current law, that is KCL, right? So whenever any steady current flows in a circuit, when there is neither any accumulation of charge at any point in the circuit, nor any charge is removed from there, right? So we can say that Kirchhoff law is simply can be used as a statement for the conservation of charge. Then comes the Kirchhoff's second law, or this is also called the loop rule. This is called loop rule. What does it say? It says that in any closed loop, of the given circuit, the algebraic sum of the products of current and the resistance, that means IR, I and R in each part of the loop is always equal to the algebraic sum of the EMF in that loop. That means we say sigma. If we have so sum of, let me say, sum of IR should be equal to sum of EMF, right? The most important thing in this is we have to be very careful while selecting the loop, and most importantly, the direction of the loop. So we know that current always flows from positive to the negative of the battery. So whenever you are to draw the loop or you are to select the loop, you can select loop in any of the directions, but you have to be very careful by taking the direction of the current. So it should be from positive to negative, right? Like, so for that, there are certain sign conventions to be used. What are these? That when first one is, say, when we move along the direction of the current, right? The product of current and the corresponding resistance and the corresponding resistance, that is IR, is taken as positive. And when EMF is taken positive, suppose like in this loop, this is say E1. E1 is shown from moving from negative to the positive terminal. It is taken as positive. And if it is taken from negative, in this direction, then it is taken as negative. Here it is taken from this to this, so it is taken as positive. So this is the loop. We can select loop either in this direction or in that way, clockwise or anti-clockwise. That depends upon you. You can select any loop in any of the directions, but be careful about using the sign conventions. And the base of that is select the direction of the current, in which the direction of current is flowing. We need to take the sign conventions of this IR and EMF accordingly. Right? Now, so the second law says the EMF is taken as positive, right? When we traverse from the negative to the positive electrode of the cell to the electrolyte. Right? I hope it is clear. Now, like in this figure, wait a minute. Let me disconnect this all. Paste it over here. Okay. Now, in this figure, say there are two cells of EMF E1 and E2. There are three resistances having values R1, R2, and R3. And say if the current flowing in R1 and R2, R1 and R2, we say I1 and I2. Right? I1 and I2. Then using Kirchhoff's first law of the junction at A. So we have at A using Kirchhoff's first law. So we can using Kirchhoff's first law. Let me say right here first. For example, looking at figure. And using Kirchhoff's first law. Kirchhoff's first law at the junction at A. Junction A. The current flowing in R3. This is R3. So this I1 is coming from this direction, this I2 is coming from this direction. These two will be combined. And here we get I1 plus I2. So at the junction A, we can write the current flowing in R3. The current flowing through R3 will be I1 plus I2. I1 plus I2. Right? Let's do this. This is the total current which is flowing through R3 at junction A. Fine. Now we have two loops over here. This is say above one is the loop 1 and this one is the loop 2. Now using Kirchhoff's second law, so using for the two loops, loop 1 and 2, say 1 and 2, using Kirchhoff's second law, or case loop rule, we have say if we look at this, see the direction of I1. This is the direction of the loop we have taken. Here it is. So they in this direction, fine. This I1 is moving in this direction through R1. So we have I1 R1. Then this is I1, fine. And here, when it comes in this direction, this is the direction of current, and I2 is moving in this direction. It's shown over here, and this current is loop we have taken this way. So here we'll take minus I2 R2, right? And EMF, if we look at this EMF, this point, this is pointing from negative to the positive, so it will be taken as positive. And here E2 is in the reverse direction of this. It's moving against it, so we'll take it as minus. So in all, we'll write over here that using Kirchhoff's second law for loop 1. So for loop 1, we have this is I1 R1, then minus I2 R2. This is equal to, sorry, shit. Sorry. This is equal to, say, E1 minus E2. Fine. This is for loop 1. Now, similarly for loop 2, for loop 2, we have, this is the, here we are considering this loop 2, this one. So in this way, here the current is at junction A, the total current we have is I1 plus I2. So I1 plus I2 is flowing through R3 and I2 is flowing through R2, right? So they both are in the same direction of the loop. So they will be taken as positive. And EMF here, there's only one cell for this loop, which is having an EMF of E2, right? So this will be written as I2 R2 plus we have currents I1 plus I2 into R3. This is equal to E2, right? Fine. And this is Kirchhoff's second law, loop rule. It's dealing with the voltage. It's dealing with the voltage. So it's also called KVL or Kirchhoff's voltage law. Or we may write as Kirchhoff's voltage law or KVL. First law is called KCL, Kirchhoff current law. This is called Kirchhoff voltage law. I hope this is clear. So using these tactics, by selecting the loop, we have to find, while using this Kirchhoff law, so be very careful at junction. We can apply the junction rule, which is applicable for the current, right? Total current कितना जा रहा है, कितना आ रहा है, वो same रहेगा. जितना भी करंट एंटर होगा जंक्शन पे और जितना करंट लीव करेगा जंक्शन को, देयर सम इज ऑलवेज इक्वल टू सेम, दे आर इक्वल. एंड फिर हम देखेंगे कि आई आर की जो वैल्यू है मींस द करंट विच इज फ्लोइंग थ्रू एनी रेजिस्टेंस, जितने भी उसमें लूप के अंदर वो आएंगे उन सब का सम शुड बी इक्वल टू द टोटल ईएमएफ ऑफ द सेल्स इन दैट पर्टिकुलर लूप. वो सब लगाएंगे, देन विल सॉल्व. तो हमें इसमें डायरेक्शन का सबसे ज़्यादा ध्यान रखना है. एंड जो डायरेक्शन है वो करंट का, मैंने जैसे आपको बताया कि पॉजिटिव टू नेगेटिव हम शो करते हैं, तो हमेशा पॉजिटिव टू नेगेटिव वो लेना है, उससे हो जाएगा. नाउ विल कम फॉर व्हीटस्टोन ब्रिज. तो व्हीटस्टोन ब्रिज अरेंजमेंट जो है, इट इज फॉर द रेजिस्टेंसेस बाय विच द रेजिस्टेंस ऑफ एनी गिवन कंडक्टर कैन बी डिटरमाइंड. right? So this is an arrangement of resistances to calculate the resistance of any given conductor. So in this, we have 4 resistances. So they are so connected as they form the parallelogram. In one diagonal of this parallelogram is connected a galvanometer, as we can see over here. Galvanometer detects the presence of the current, right? And now, if the resistances in the 4 arms of parallelogram are so adjusted that on sending current in the bridge by the cell, there is no deflection in the galvanometer, then we can say that the bridge is in the balanced condition. Means when this K2 is closed, there should be no current flowing through the diagonal BD, and this galvanometer should show no deflection. Then we can say that this is in the balanced situation. Right? In this condition, the ratio of the resistance of any 2 arms of the bridge is equal to the ratio of the resistance in the remaining part of the adjacent arms. Right? Like we can see here, P, Q, R, and S. These are the 4 resistors which are connected in the form of 4 arms of parallelogram A, B, C, D. Fine. And between B and D is the galvanometer connected over here. And A and C are connected through cell. Through cell. And we have 2 keys. One is K2 and other one is K1. When we press the key K1, current I will start flowing from the cell. Here at A, this current is divided at this position. A, this is divided into one part, this I1, and here it is I2. It is divided into 2 parts. One part I1 flows through arm AB, and this part I2 flows through arm AD. Right? So these 4 resistances, which is P, Q, R, and S, they are so adjusted that when we press K2, this deflection in this galvanometer is 0. It should not show any deflection. That means no current flows through this in the diagonal BD. Now the same current I1 will flow through this resistance Q. Same current flows through I1. The same current I1 will flow through this arm BC or this resistor Q. And the same current I2 will flow in this arm DC. In this arm DC. Fine? So when we'll press this key K2, there is no current flowing through AD. Now, using Kirchhoff's second law for the closed loop, which loop ABDA. For loop, we have ABDA. ABDA. Right? Using loop rule. I1P, so direction is from this clockwise. So let me draw this. So we have let's say it is moving in the clockwise direction. Right? So we using loop rule. We have I1P. Now, as we can see, I2 is moving against the direction of the loop. So we'll take minus over here. minus I2R, right? This equals to 0. Or we may say I1P is equal to I2R, right? And similarly, for the closed loop, this one B, C, D, B. B, C, D, B. We have I1Q again in this direction. So I1Q minus I2S, I2S equals to 0, or we may say I1Q is equal to I2S. Let's say, let us say for our convenience, let this be equation 1. And this we say equation 2. Now, dividing equation 1 by 2, we get I1P divided by I1Q. This equals I2R divided by I2S. Fine. And we get P by Q equals R by S. R by S. So this is the principle of Wheatstone bridge. Right? We can see that the ratio of the resistance P and Q, the resistance and the resistance say R, they are known, and let's say S be the resistor for which we are calculating the resistance, we can calculate it. Fine. So these arms P and Q, they are called the ratio arms, and this arm AD, this arm AD is known as the known arm, and this arm CD where S is connected, this is called the unknown arm. And when the bridge is balanced, fine, then on interchanging the positions of the galvanometer and the cell, there is no effect on the balance of the bridge. Then we may say that arm BD and arm AC, which are the diagonals, they are called the conjugate arms of the bridge. And the bridge is maximum sensitive when all the four resistances are of the same order. So this is the point to be noted, that the value or the sensitivity of the bridge, we may say, the sensitivity of the bridge depends on upon the values of the resistances. The bridge is maximum sensitive when all the four resistances are of the same order, right? Now, meter bridge. So meter bridge is actually based on the principle of Wheatstone bridge. And it is used for the determination of the resistance of the conductor wire. You must have done in the practicals also, and you will do in the practicals, right? So this is based on, meter bridge is based on, the bridge is based on Wheatstone bridge, on the principle of Wheatstone bridge. Right? So as we can see this in this figure, meter bridge. Right? Here, AC is 1 meter long wire. From this to this. AC is 1 meter long wire. Right? And it is made up of magnenin or constantan. And that is fixed along the scale on a wooden base. You must have seen Wheatstone, this meter bridge in your labs. And the area of cross-section of the wire is always same at all the places. Means it is of uniform cross-section area. A and C, these ends of the wire, they are joined to the two L-shaped. So one and this two. These are L-shaped corners, copper strips carrying binding screws as shown. यहाँ पे दिखा भी रखे हैं, right? Now in between these strips, there is a gap on either side, and then there is a third copper strip which has 3 binding screws as they are shown by dark circles, right? So middle screw, which is D, it is connected to the sliding jockey B. So jockey is movable, fine. Jockey B, and it is connected to the jockey through the shunted galvanometer. Shunt is always provide us the lower resistance, and it's connected in parallel. The knob of the jockey can be made to touch and move on this wire anywhere. Now suppose we want to find resistance of, say, wire, any wire, right, which is connected across the gap between, say, C and D. So this is the S. This S is the wire whose resistance is to be found. We'll connect this in C and between the C and D, and there is a resistance box which is kept across the gap between A and D. So between this A and C, they are connected in, there is connected a cell, then a rheostat, and a key. So when the sliding jockey touches the wire, say AC at, let's say at point B, right? So we can say this wire is divided into 2 parts. The 2 parts are AB and BC. So they will be acting as resistances, say a P and Q of this Wheatstone bridge, like Wheatstone bridge. If we compare it to this, so these are the 2 resistances. So of length AB and length BC. Fine. Now, first of all, what we will do? We'll have a resistance R, which is taken in the resistance box, and we'll close the key. The jockey is slide along the wire AC, along the wire AC, and we will determine a point such that on pressing the jockey at that point, there is no deflection in the galvanometer, right? Means it is in the balanced situation. So, and in this position, the point B, this B, and point D, they are at the same potential. No current flows through this. So there will be no deflection in this galvanometer G. At this point B, where it is happening, or where galvanometer shows no deflection, this point B is called null point. And we'll find the length of both parts AB and BC. Let's say AB is L, right? And BC is, say, BC will be 100 minus L, right? Now, suppose the resistance of the length AB of the wire is, say, P, and that of the length BC is, say, Q. So then, by Wheatstone's principle, Wheatstone's bridge principle, or by principle of Wheatstone bridge, Wheatstone's bridge, we have P pi Q equals R by S in the balanced state. And let's say length of ABB, and let the length of ABB, say, L centimeter, then the length BCB 100 minus L. 100 minus L centimeters. Right? So resistance of AB. So resistance of AB, that is P, its value is given by, so this is equal to resistivity L by A, L by A, and resistance of BC. BC, which is, say, Q, this is equal to we have rho sorry 100 minus L divided by, say, A, area of cross section, right? So where rho is what? It's nothing but specific resistance of the material, where we say this rho is the specific resistance or resistivity, right? And A is the area of cross section. So resistivity is in measured in ohm centimeter. You say ohm centimeter. And area of cross section A जो है that is taken in centimeter square or square centimeter. The area of cross section. So using Wheatstone bridge, we have P by Q equals L by this is 100 minus L, right? And if we use this value P by Q and put here, we can have this is equal to, let me say, let's say, so equals L by 100 minus L, this is equal to R by S, right? Or let me say S is equal to R 100 minus L divided by L. So when we take R resistance in the resistance box and L is the length we measured, the value of S resistor can be calculated using this formula. Right? So this is how we use Wheatstone bridge to find the unknown resistance in the meter bridge. So there are so I think with this chapter is over, we may say, and we'll start with the new chapter tomorrow. That's magnetism.